today we're going to move into reinforcement learning. We basically finished the basics of MDPs. We saw the basic algorithms, the basic framework, and now we're going to look at a situation where you don't know the MDP. And really, reinforcement learning is applied in a couple of different situations. So one is this situation where you don't know the MDP. You just have the ability to walk around in it. And the other is sometimes you apply reinforcement learning even when you know the MDP, but it's a really big problem. We'll talk about that. So, for example, AlphaGo, if you're thinking that that's like a pure reinforcement learning system, which you could argue that whether it is or not pure reinforcement learning, but AlphaGo, do we know the model of the MDP for Go? Right, it's just a game, right? It's a game rule. So we know for every action, you put a piece on the board changes according to that piece. So we know a model for Go, yet they apply reinforcement learning to it because it's an approach that's sort of a scalable approach for getting a policy for Go that allows you to leverage function approximation. So let's talk about this a little bit. So this is what we've talked about before. We know a model, I give it to you, you solve it with value iteration or policy iteration. The unknown model situation is more like this, right? You usually in Markov decision processes, you'll assume you know the state space, or at least the representation of states, and also in any state you can get the set of actions, but that's all you start off knowing. You don't know these transitions that are missing here, or the rewards that are missing here. Okay? And you just have to wander around and figure out how to actually act in the world. So what could you do if you have an unknown MDP model, right? So all you can do is act in the world. Well, one thing that's often done in control engineering would be this option one. So we're gonna hand code some parametric form of an MDP model, right? It might have some parameters. In robotics, this might be a linear model. In other applications, it might be a different form of model. But you're going to hand code that, and then you're going to collect some data somehow from the environment. And we won't say how you collect the data. And then you're going to tune the parameters of the model to match the data, right? So the data is going to give you a whole bunch of examples of, here's a state, here's a transit, here's an action, and here's the next state. And that's sort of a supervised learning problem once you have all that data, right? So now in control engineering, this is often called system identification. Right? You're trying to identify the system. Reinforcement learning, you can think of it as trying to do that automatically if you're taking a model-based reinforcement learning approach. Like it's trying to wander around and learn a model of the world that's good enough to take action, to allow it to take good actions. And some reinforcement learning, as we see, is going to be explicitly trying to learn a model, and some does not. Some will try to bypass model learning altogether. So those are sort of the two options, and option one is very, very common in the real world. Right? This is what you do often in robotics. You're trying to tune the model. If it's a little bit off, you run the robot a little more to collect more data, and so on and so forth. So the other situation that we mentioned was when the MDP is enormous, and in particular when it's so large that you could not enumerate the states and run what we call table-based value iteration or policy iteration. Right? So when we say table-based, we're basically meaning that you are enumerating all the states in the transition matrix and whatnot, and that the basic constraint is you've got a memory constraint first of all, and also you do have a time constraint because these algorithms have to iterate over every individual state. Right? They scale polynomial in the number of states, which in some cases is going to be way too large. So So that's sort of the problem with enormous worlds. Um, so it's worth spending a little time talking about, well, different ways of dealing with enormous MDPs, and we're going to focus on reinforcement learning mostly in this class, but it's good to see at least there are some other ways. So model-based planning is one approach, and this I probably talked about this um, earlier. But so model-based planning, what we've learned so far in this class won't work for the enormous ones, right? Because they scale in terms of the number of states. But there are other techniques where you're going to, instead of writing down the MDP as a flat MDP model, in other words, a model that has a size that's related to the size of the state space, you're going to use a language to write down the rules of the MDP that is compact. And so we can write down the rules of Go in a document about this long, even though the game of Go is enormous, right? And so we're very used to that. Like every game we play is enormous, but you learn to play it by reading the rules of the game, and they're exponentially smaller than the size of the game, right? That's what rules allow you to do, describe very large systems very compactly. And so there are different languages in AI for writing down MDPs in a compact way. One of these languages is called RDDL. Sometimes people use dynamic Bayesian networks, and there are languages for describing those. But at the end of the day, given that language, you then have to have an algorithm that can use the language to come up with policies. And those are often pretty complicated and tricky. We may get to them at the end of this course. There's some really interesting things. For example, there are ways of trying to do value iteration or policy iteration symbolically, right? So some of you might be familiar, for example, with symbolic integration, where Mathematica, for example, here's an integral. You don't want to just solve it for a particular case. You want the general form. There's analogous things you can do for Markov decision processes. If you have a rule-based or symbolic description of the MDP, you can come up with a symbolic description of the value function that's much more compact than listing out all the states. And you do value iteration on the symbolic representation, and so one iteration you'll have a symbolic representation, and then you'll apply a Bellman backup, a symbolic one that gives you the next value function. And the problem is that these will often even the symbolic representation will blow up if you run this long enough. But there's some interesting work there, and we've done a lot of that work here at OSU in the past. We're also, in this class, we will talk about this other approach for enormous worlds, which we'll call Monte Carlo planning, which this is sort of you could say this is what AlphaGo is doing when it's making its decisions. It's forming a search tree by doing lots and lots of look ahead, running trajectories. And so basically when you get into a new state, you can think of the system as doing a little bit of thinking, maybe a lot of thinking, by looking at the future in many ways and then finally making a decision for this state, what action to take. You take the action, you get to the next state, and then you do a whole bunch of trajectory simulation again. And this is something that I'll call Monte Carlo planning. And the nice thing about this is it only requires that you have a simulator of the MDP. You don't have to have a nice, compact language description of the MDP. So it could be that the MDP is only described via some giant C program that gives you a simulation. And there's a lot of situations where you have a simulator, but you don't have a nice description in a formal, compact language. So we'll talk about this class of algorithms later on. If you've heard of Monte Carlo tree search, that's where that sort of thing will be covered in that part of the class. So finally, reinforcement learning is a very popular way of dealing with very large MDPs. And this is really because of the function approximation ability, and we'll be talking about this. So reinforcement learning tries to compactly represent a policy or a value function via something like a neural network or a linear function approximator or a decision tree, however you want to represent it. But you're not going to represent it as a table, you're going to represent it as a compact functional form. And reinforcement learning, there are various ways of trying to do that. Often works well for large problems in a whole bunch of domains. But there's also a lot of limitations. It's not a panacea by any means. So we'll be getting to this, but we're going to first deal with reinforcement learning for small state spaces, which may be disappointing to you at first, but that's where the basic algorithms can actually be analyzed and have any sort of guarantees. And really, what's called deep reinforcement learning is nothing but those basically small state space algorithms. And instead of updating tables, you update function approximators. And for deep reinforcement learning, it's a deep network, and that's why they call it deep reinforcement learning. So really, once you learn the basics of the table-based methods, you'll have learned most everything you need to know to move to the deep reinforcement learning setting, or just with function approximation. All right, so we'll now just get right into reinforcement learning. So as we said, we have no knowledge of the environment beforehand. All you can do is take actions in the world. And this is difficult for many reasons, right? Reinforcement learning is hard, and really impossible for a lot of problems. You could say, So one thing, every time you take an action, if it's a stochastic world, you could have a different effect, right? That's just naturally confusing, and you can imagine that the more random your actions are, the harder it is to learn. And of course, at some point, if your actions are random enough, you really can't do anything useful in the environment anyway. So ironically, sometimes when the most random environments are actually not that hard to learn in, because like the bar for how good you can do is pretty low in the first place. Sometimes the hardest problems are these highly deterministic problems where you have to find these detailed paths to a goal or something, because it's kind of like trying to find a needle in a haystack. Whereas if everything's extremely random, well, you can't really plan far ahead anyway. Right? There's too much randomness. But non-determinism does make the world more confusing, for sure. Rewards and punishments that you're getting when you act in the world can be infrequent, and this is one of the biggest challenges of RL. So if you're trying to use reinforcement learning to play chess, and you only get a reward at the end of the game that says, "Hey, you won," or "You lost," or "You had a draw." That's not a lot of information, right? You took maybe 100 actions. Maybe it was a long game. You took 100 actions before that, and now you're saying you won. Well, how do you know which of these actions actually made a difference? So this is something called the credit assignment problem. And RL is really hard in that sort of environment. And usually what people will do is they actually change the problem and make it easier by adding in some reward signals that are more frequent and that give you hints. They call this shaping reward, for example. But so a lot of applying RL is often about trying to engineer the problem so that RL can be made to work. I remember, I forget when it was, maybe early 2000s. I was at ICML, and there was a talk, and I think it might have been Peter Stone and maybe Satinder Singh. They had a paper. It was called "Scaling Up RL to RoboCup Soccer," and this isn't criticizing them because they do a lot of good work. But at the end, I was left. I think they should have called the paper "Scaling RoboCup Soccer Down to RL," because that's sort of what the paper was. It's like, okay, we simplify RoboCup Soccer into a package that RL can actually solve. And that's often what you're doing when you're doing engineering of RL systems. You're trying to figure out how can I get the system engineered right so RL can do something non-trivial and yet still get good performance on the problem we care about. Because usually RL is going to be solving kind of a different problem than what you originally specified after all of these little changes. So we'll talk about some of these, and you'll get some experience applying RL later in the course, and you'll see it's not so easy. But it is something that you can gain experience and you get better at. So it's one of these engineering arts in a sense. The more you do it, the better you get at it because you get better at diagnosing what's going wrong. All right, so yeah, I guess that's that. All right, so two classes of RL. We've already mentioned this a little bit, but model-based and model-free. We're going to consider both of these. And they're actually a little bit difficult to tease apart theoretically, right? Because they're sort of model-based versus model-free. It's sort of you're talking about what is the algorithm doing, right? So model-based, intuitively, we're saying, oh, the algorithm is learning a model of the environment and using that to plan somehow, right? Maybe it's doing value iteration. Model free, we're saying, oh, it's not learning a model and it's doing something else. But this is really a statement about what's going on in the algorithm, right? And who knows, maybe something looks like it's model free, but it's effectively internally got something that is equivalent to a model, right? It feels like we should call that model-based. And so theoretically, what people do to characterize these two things is they look at the memory usage of the algorithms. So if we said something is explicitly model-based, like explicitly forming a model of the environment, and let's think about the flat state space version, where we were dealing with individual states. How much memory do we think we're going to need to use in a model-based method? In terms of the state space size, let's say.
Be proportional to the state space size.
Okay, so the policy will be proportional. If we're doing a model-based method, though, what does the model-based method have to keep track of if we're thinking of it as a pure model-based method? It has to learn the model, right? And how much memory would a model take to store in the general case? What's a model? The reward function. How much memory do you need to store the reward function? Yeah. States times actions, right? That much memory if it's a state action reward function. How about the transition function? So transition function is a square thing, right? A bunch of squares. So the state space squared, right? Size of the state space squared times A, right? Yeah. So if you're going to learn a model explicitly in the flat case, you're going to need memory that's sort of proportional to the square of the number of states, right? A model-free method, if it bypasses all that, it should only need to use memory that's proportional to the number of states, linear in the number of states as opposed to the square. And so all this is just to say that theoretically, when people are analyzing these and they're trying to say, hey, is there a formal property for a model-free algorithm? They characterize model-free by whether it's linear or quadratic in terms of its memory usage in the state space. Okay? So model-free, you would only be able to use linear memory in the number of states. Model-based, you're allowed quadratic memory. All right? So that's just a theoretical distinction, but it's kind of a deep point because I could call something model-free, but maybe inside I'm doing something that's very much model-based because I've got this big matrix that I'm keeping track of. Uh, all right, so we'll consider both of these, and we're going to start off on model-based because that's more naturally following from what we just did, which was, well, we assumed we had a model, and what do you do with it? All right, so yeah, we'll deal with this. So we're first going to study RL for small MDPs, and small means that you can enumerate the states more or less, and then we're going to move on to large MDPs, and we'll just move these into here with function approximation. All right, so how can we learn a model from data? Right, it's actually relatively straightforward. So suppose that you've got a data set of an MDP. So you've been running around in the MDP for a while. What does each piece of data look like? Right. So each data tuple. So we're often going to be dealing with data tuples. You're going to have a state that you were in. This is the action that was taken. This is the reward that you got, and this is the next state that you ended up in. And so if you've run around in an MDP for a while, the data set you get are tuples of this form. Okay? So that's pretty straightforward. So if I give you that whole set of tuples, how can you estimate the model of the MDP? Right? And it's not really a trick question. Any ideas for how you would do that? How would you estimate the reward function? This is definitely not a trick question. So if we assume, so I'm giving you a whole bunch of data of this form, and now I want you to just give me an estimate of the reward function. Right? And what we've assumed is a deterministic reward function, right? And so we're not doing any function approximation. We're just representing the table, right? We have this tabular reward function. For every state action pair, it needs to give a reward. So if I give you this data, what are you going to do?
Fill in the table with the samples that you see.
Yeah. So if we saw state S and action A, and then R followed it, RSA equals R, right? So there's nothing to it. That's straightforward. So there we have it. And for any reward, any state action pairs that you haven't experienced, you would just have to set the reward function to some default value, and it might be 0. We'll talk about later how setting the reward to an optimistic value has some nice properties later on. All right, so how about the transition function? How can you estimate the transition function using this data? Right? Each of these is an example transition, right? I took A and S, and I saw S prime after. So any ideas?
Count and divide.
Okay, count and divide, right? So I was in state S. So our estimate for this, this is there's nothing complicated here. It's just frequencies. So what's our estimate of being in S, taking A, and ending up in S prime? Well, that's the number of times that you saw this tuple divided by the total number of times that you were in S and you took action A, right? Because every time you're in S and you take action A, you may end up at a different place. If it's deterministic, you'll end up at the same place, and your estimate will be 1. And of course, you have issues of 0 counts here. There are lots of ways to deal with that. For example, you could add a constant to the denominator and numerator if you wanted to, but we won't deal with that right now. All right. So, yes.
Why are we not summing up over all states in the reward function?
And the reward function.
Because you can give one reward issue as stats, another reward.
Yeah.
Oh, okay, fair enough.
So the assumption here, I didn't make it explicit, is that we're assuming that we're in an MDP that's modeled as we've defined in the earlier slides, and the reward function was deterministic, so it will always be. If the reward is random, this model also works for this. you can still collect experience if the reward function is a random function of state action pairs, or if it depends on S prime. Then you're going to have to do some averaging here. Right? It would be the average reward you saw after you took action A in state S. All right. Okay, so pretty straightforward. I give you a whole bunch of data, tuples, and you can estimate a model, right? And that means that using that estimated model, you could apply policy iteration or value iteration, and there you have a policy, right? So this gives you your first naive model-based algorithm. Act randomly for a very long time and collect all your data, right? Collect tuples. And maybe you have some fancy way of being less than random, but let's just say you act random. You learn the transition and reward function. That's nothing more than the estimation that we just talked about. You apply policy or value iteration, and you return the policy that you get. So will this work? Is this going to work as an algorithm in general? Any reason why it might not work?
Depending on the problem, you might not be able to act randomly for a long time.
Okay.
For example, if you take driving cars, you cannot randomly drive for a long time.
Yeah. So yeah, it could be dangerous to act for a long time, and you may just die, or you may get stuck somewhere. Like you may just get stuck in a corner or something. So if so this does have problems, and this slide is showing the issue that can come up. So if you were to start your RL algorithm right from scratch, and you start in S0 and then you take A0, if you end up here, this is what we call a dead end, right? Right. So it's a dead end. I don't have the reward function here, but it's reward 0. And once your agent ends up there, you're kind of hosed, right? There's nothing it can do. It can't learn any more about the rest of the MDP. And this is analogous to you have an RL agent driving a car from scratch, and it drives off the road and crashes, and that's the end of its learning. That's why we don't run RL from scratch on cars or most anything physical, really. So this is sort of the first fundamental issue. And whenever there's theory that's dealing with RL, RL theory always has to assume that the environment is sort of connected and there are no dead ends, because otherwise you can't do any theory, right? All you can say is, well, there's a possibility you're gonna get stuck. All right, so for the most part, RL theory will assume no dead ends. When there are dead ends, that's usually, in a lot of environments, you have to take that into account if you're going to be training something in the real world. Usually you're going to have to set up the environment so if it does reach an impasse, you can reset it. You can do this in simulation very easily, as long as you can detect sort of these situations. In the real world, it's a lot more difficult. People do talk about they talk about different forms of robust RL and safe RL that can act in environments from scratch without having problems, but they all will have their own assumptions, right? There's nothing, if you make no assumptions, there's nothing that can prevent the world from whatever action you take just falling off a cliff, right? I can create an MDP where that's going to happen. And so you have to make assumptions to avoid that sort of thing. And they'll make assumptions such as smoothness assumptions. Like if I'm in this state and I took this action and things were okay, then similar states and similar actions, according to some definition of similarity, will also likely be okay. And they try to get by that way. But without assumptions, you can fall off a cliff at any moment, and that's all there is to it. So, be careful when you're applying RL in the real world without going through simulation first, and even then. So now, if we assume there's no dead ends, will this work? And I gave you the answer, yes. But So does it seem like it should work if there are no dead ends? Right? No dead ends means that you're always going to, if you act randomly, you're always going to get to a state in an action and be able to try it forever, right? There's no time when you can't reach a state in an action pair because then you've sort of reached a sort of a dead end region of the MDP. So no dead ends means that you can always formally means that you can always reach any state action pair, right? And then you're guaranteed if you run long enough, you'll collect enough data for all state action transitions that you'll get an accurate model of the MDP, and the policy you solve for will be good. Okay, so that's straightforward. Are we happy with this, or what would be your concern about this type of approach? Right, because this is a solution, presumably.
Could there be any worse things that you have to take a lot of time until you can switch that and accident?
Yeah, so it's kind of stupid, right? It's not using any knowledge that it's gained along the way ever, right? It's just acting randomly, and then it's saying, okay, now I'm gonna think, and I'm done. As opposed to maybe it should be collecting some experience and doing something with it to help it learn more quickly, perhaps by, for example, trying to get to states that are hard to get to, and learning about them. So that's sort of the main problem. It's going to act randomly for a long time without exploiting any knowledge. But this would be an approach that converges, and it's worth at least thinking about. What can we do now? We can revise this, and you could say we're going to start with some uninformed model, like it's just an initial model somehow. We're going to solve for that optimal policy in the initial model, and then we're going to run the initial model, right, for a while. We're going to run that policy. Maybe we just execute one action suggested by it. Maybe we execute a whole trajectory. And then we're going to update the model based on the observed transition, right? So we're going to learn a little more. And then we're going to solve for the optimal policy with that new model. We're going to execute it and learn a little more and solve for the optimal policy. That seems like a pretty good idea, right? You're incrementally improving your knowledge. But will this have any problems? This approach here? Right. If we think about it, what it's doing is, restating it, it's kind of a greedy approach, right? It's always acting greedily with respect to your current model. That's how we'll characterize it, as opposed to always acting randomly during learning. And so do you see any problems with this?
If it encounters a reward, it will continue to seek out that reward if it gets reinforced enough.
Yeah. So what he's saying is you could encounter like a tiny little reward, and that looks pretty good, right? If your initial model, for example, initialized all rewards to 0, like a tiny little reward is better than 0, and so your greedy policy would be like, hey, I'm going to go get that tiny little reward, and you could just be stuck. So you can very easily get stuck doing this, and we'll show this. And just intuitively, if there's a penny on the floor over there, and there's a pot of gold over there, and I find the penny first, and I never really, and I act greedily, let's just say that's an infinite supply of pennies, with discounting. I would just keep going over there. That would be my policy, as opposed to, well, I should be exploring and going over there. So that's the problem, and this MDP is one example. It's just showing you a concrete example of where that can happen. So this is the true MDP. Okay, so when you're talking about model-based methods, it can get confusing because there's always like the true MDP, which is sort of the true world that you're acting in, and then there's the MDP in the agent's head. Okay, because the agent has its own model of the MDP, and they're never going to be exactly the same, but you're trying to get them close. So this is the true MDP, and let's suppose our algorithm started out here. We don't know what the algorithm was doing or why it was doing it, and then it took A1 and got 0 reward. Then it took A0 and went to S1 and took A0 and got a negative reward. Okay, so that's what our algorithm saw so far. So it saw that, oh, I take A1, I get 0 reward, and then I went here and ended up getting a negative reward. Okay, so that's what it learned so far. Now, if we look at, let's say we initialize, this is the MDP model in the agent's head after that experience. Right, so what I'm saying here is I initialized everything to 0. The rewards were initialized to 0. And the transition function was also initialized to something trivial. Like we just initialized the transition function to essentially be a no-op. Like every action is assumed to be a no-op until we see it's not. And so, for example, we never took an action in S2, so these are just no-op actions, and they have reward of 0. Now, we did collect data for A0 here, right? We saw it had a reward of -1. We only saw one transition, so we're going to say that has probability 1. And we collected data here too, and that was still 0. And so from S0, what's the optimal policy going to be here? Would you say?
Just taking A1 over and over.
Yeah, just take A1 over and over. I mean, you could say that another solution would be to take A0 and then take A1 here, but the simpler one is just take A1 here. And that's clearly bad, right? We know with this original MDP, well, it's one of these MDPs where we kind of want to get down here, right? We want to take A0 until we end up here, and then we would be really happy. We just take A0 over and over. And so the model-based approach is now stuck, right? Because, okay, I'm going to act greedily. I started at S0 now, and then it's just going to keep doing this. It's just going to keep doing this. It doesn't collect new data, right? All the data points it collects are going to be identical, and so this model never changes. We never learn any more. We just go around in a loop forever, right? So that's just showing you an example of where you can get stuck. Even though there's no real dead ends in this environment, there's a problem essentially that you end up in a dead end because of your own sort of ignorance. All right. So now we can revise that, right, to try to avoid the problem. So obviously the problem is we're acting greedily. So we probably want to not act greedily all the time, right? That's sort of the idea. And what this brings up is a notion of exploration, right? And this is a lot of times people will say, exploration versus exploitation is one of the key things in RL that you have to deal with. But exploitation means that you're essentially exploiting your knowledge. That's sort of greedy acting, right? And exploration means you're going to try to get more information. You're not going to act greedily for the purpose of getting more information about the world. So that's basically it. And managing that trade-off sort of dictates how quickly you're going to learn, and how suboptimal you might be after you stop effectively learning. But generally, what happens is most of these algorithms will explore more in the beginning, and then slowly decrease the amount of exploration to sort of focus on the more promising actions and states in the environment. And we'll see how this works. But that's roughly speaking how most RL algorithms will work. Even deep RL, they'll usually have an exploration parameter that you might call it a temperature parameter that you crank down over time, and the system becomes more exploitive as opposed to exploratory. In a lot of systems, will just they'll just start out acting completely randomly for a long time, and then they'll actually start with some principled exploration. All right, so this brings us to this slide, this refinement. So you start with an initial model, you solve for the optimal policy in that model, and now you're going to take an action according to an explore-exploit policy, as opposed to a greedy action according to the optimal policy. Then we're going to update the model and go to step 2. Will this work? I guess it's not a fair question because this is a pretty vague notion, right? It depends on the explore exploit policy. Can somebody think of one property that an explore exploit policy should have for this to definitely work? Assuming there's no dead ends. So what's one property?
It should continue to explore until all the states have been explored at least once.
Okay. Now so it should definitely continue to explore. Now is exploring every state just once enough?
At least once. Not sure. Because there may be different transitions.
Mm-hmm. Yeah.
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 In infinite time, it takes every state action pair an infinite number of times.
Yeah, so we saw that one way that guarantees correctness is you act randomly for a very, very long time. And so we effectively, to make explore exploit policies sort of work, you always need to guarantee that it's never the case that there's a state action pair that your explore exploit policy will not be able to reach. Right? So it's always the case that there's a non-zero probability that you'll be able to take a certain state action pair. And you can trivially do that, for example, by every now and then taking a random action, right? Because if every now and then you take a random action, there's no dead ends, you'll eventually get everywhere at some point. It may take a very long time. But theoretically, that's how you would solve this issue. So that's sort of the basic property. We will this will be formalized a little bit more in a moment. But we're going to talk about some explore policies now, and here again I'm going to reintroduce the Q function. In reinforcement learning, this is a very, very important function we'll see. So again, the Q function, and this is the Q function is basically estimating the value of taking an action in a state, right? As opposed to just estimating the value of a state. And so you could be in a really good state, but there could be a really bad action, and the Q function will return a bad value for that action in that state. But it's simply what you would expect. I'm missing an A there, but it's the immediate reward plus what you expect to get in the future. And this is our estimate of the value in the future. All right. Now, and the greedy action is the one that maximizes the Q function. All right. Oh, and I guess we're pretty much out of time. So next time we'll continue doing this, and we will get that assignment out to you, and I'll make sure you have enough time to do it. I'm going to probably give you a week and a half for this. Not because I think the initial part will take that long, but I want to give you a little time to explore that competition task that we're giving you. All right, so we'll see you on Friday.